Hi guys, welcome to my YouTube channel Fundamental Chemistry. I hope you all are well. In this video, we will learn pericyclic reaction, and in my ongoing videos, we will learn a complete pericyclic reaction. So for pericyclic reaction, molecular orbital theory is very much important. So if you watch out my earlier video on molecular orbital theory, then definitely you can understand pericyclic reaction. If you don't watch, so please again watch it and then come to here. So there are three types of pericyclic reaction: electrocyclic reaction, sigmatropic rearrangement or reaction, and cycloaddition reaction. So before going to electrocyclic reaction and others, we will learn how to draw bimolecular orbital diagram of organic compounds. So let us take a molecule ethylene, in which there are 4 CH or carbon hydrogen bond, 1 sigma bond and 1 pi bond, and this sigma carbon hydrogen bond is formed in this way. So we can write MO of carbon hydrogen bond. So this is the p orbital of carbon. This is the s orbital of hydrogen, and combining they form. And when the orbital overlap in phase condition, that is they are of same phase. Here you can see the plus, and here s orbital has also the plus. So they produce sigma orbital. We get sigma bond. And when they overlap in out phase condition like this, they produce sigma star molecular orbital. This is like that. This is due to the electronic repulsion between these two electronic cloud. So this is of high energy. That is why this form antibonding molecular orbital and is called sigma star molecular orbital. Again, we know that how to draw molecular orbital of carbon-carbon bond. Here again we will have p orbitals of two carbon atoms, and when they overlap in phase condition, that is of similar phase, they create this structure. This is the cylindrical charge density, and this is called sigma molecular orbital. And when they overlap in out phase condition, they produce this one. This is called sigma star molecular orbital, and this is antibonding again. This is due to the electronic repulsion. The two orbitals are distantly present, and due to the high energy, this is called sigma star antibonding molecular orbital. So now we will see how the carbon-carbon pi molecular orbital is formed. So molecular orbital of carbon-carbon double bond. So in this case, two type of overlap is possible, and we also know that pi bond is generally formed by the sideways overlap of two p orbitals, and if the orbitals are along the same axis, then the overlap will be the best. So in this case, there are two p orbitals, and when they overlap side to side along the same axis, Z axis, and in phase condition, that is they are of same phase above and below the plane or axis, it produces this structure. This is due to the attractive force between the two lobes that are of same phase above and below the plane, and this is called pi MO by pi molecular orbital. And when they overlap side to side in out phase condition, they produce pi star molecular orbital in this way. Again, this is due to the electronic repulsion between them, and this pi star MO is of higher energy than pi molecular MO, and this is called pi star antibonding molecular orbital and this pi bonding molecular orbital. So for ethylene, we can say that there are two types of bond or orbital is formed through carbon-carbon single bond and carbon-carbon double bond, and they are pi and sigma molecular orbital and pi star and sigma star molecular orbital. If we draw orbital diagram of ethylene, we get this is due to formation of sigma molecular orbital. This is due to formation of bonding pi molecular orbital. This is due to formation of anti-bonding pi star molecular orbital, and this is due to formation of sigma star anti-bonding molecular orbital. So we know that in ethylene molecule, the carbon-carbon single bond or sigma bond has 2 electrons. That is why we write 2 electron in this form. And we also know that pi bond, carbon-carbon pi bond, has also 2 electrons. That is why we write 2 electrons in pi bonding molecular orbital. So this is the overall molecular diagram of ethylene. So this is the highest occupied molecular orbital. Highest occupied molecular orbital, that is HOMO, and this is the lowest unoccupied molecular orbitals. These molecular orbital, due to high energy, remain in vacant form. Now, if you have said that why electrons occupy these 2 places only, because you know that in molecular orbital theory, the electrons occupy the molecular orbital like the same in which way electrons occupy the atomic orbitals. So in atomic orbitals, the orbitals are filled by maintaining Pauling principle, Moore's rule, Aufbau principle. Similarly, these 3 principles, that is Aufbau principle, Moore's principle and Pauling principle, also applied to it. So this is the energy that is with increasing from sigma to pi star to sigma star, the energy increases. So if we give a little bit of energy to ethylene, we will find that this electron in the pi MO get excited to this position, and thus it becomes And this singly occupied molecular orbital is called SOMO, or singly occupied molecular orbital, and it only found when ethylene molecule get excited. So this is the molecular orbital diagram of ethylene molecule, and if we only consider the pi molecular orbital diagram, then just we will write this pi and pi star molecular orbital, and just we'll simply eliminate this sigma and sigma star orbital portion. So previously in my earlier video I have to teach you how to draw orbital picture of different organic molecule, and on this video there was ethylene molecule too. So this is the orbital picture of ethylene molecule, and this is the 4 carbon hydrogen sigma bond, and this is the carbon carbon pi bond, and along this axis there is carbon carbon sigma bond. So whatever we have learned from this video, we can conclude that in case of unconjugated alkene like ethylene, pi bond formation occur due to interaction between two unhybridized pure p atomic orbitals, which lies in a plane orthogonal to the plane where sigma orbital lies. Okay, and the mutual perturbation of p atomic orbitals also generate on one bonding and one antibonding orbitals, and the bonding orbital is called pi orbital and antibonding orbital is called pi star orbital, and the pi star orbital is of higher energy than the bonding pi orbital. But what happens if there are 3 or more atoms involved in pi bonding? For example, your 1,3-butadiene, then we will have to consider extended overlap of the pi orbitals. We will come to that. So a pi electronic system derived from the interaction of n number of p orbitals contains n number of molecular orbitals, and of the total number of molecular orbitals, half will be of lower energy than the atomic orbital, and other half has the higher energy than the atomic orbitals. The lower energy molecular orbitals are called bonding molecular orbitals, and the higher energy molecular orbitals are called antibonding molecular orbitals. So if there are 4 carbon atoms, we will get 2 bonding molecular orbital and 2 antibonding molecular orbital. Now, these molecular orbitals are designated as Ψ1, Ψ2, Ψ3, Ψ4, etc. and they differ in energy. These molecular orbitals are written in increasing order of their energy as follows, where Ψ1 is of lower energy, Ψ2 is of greater energy than Ψ1, and so on. So for ethylene molecule, as there are 2 p orbitals, so 2 MO, and they are designated as Ψ1 and Ψ2. And for 1,3-butadiene, where there is 4 p orbitals, so 4 MO, and they are designated as Ψ1, Ψ2, Ψ3 and Ψ4. In my video of molecular orbital theory, I have discussed that when 2 p orbital combine to form one pi bonding molecular orbital and one pi antibonding molecular orbital, there are one common nodal plane, but there is one extra nodal plane exists for pi antibonding molecular orbital, and this is along this side. So from picture of ethylene molecule, we can conclude that when we draw the pi MO of ethylene molecule, there is no node, but when we will draw the picture of pi star MO, there is one node along this point, and the 2 opposite sides of node have opposite symmetry of 2 p orbitals. Designate them as Ψ1 and Ψ2. We can say that from Ψ1 there is no node, and from Ψ2 there is one node. So we can write that if there is n number of molecular orbital formed from overlap of n number of p atomic orbitals, Then for Shy1, there will be no node, and for Shy2, there will be one node. That is, the node follows the formula of n minus 1, where here n is equal to 1 and here n is equal to 2. Okay, similarly we will get the same thing for Shy3, and there the number of node will be 2, and for Shy4 there will be the number of node will be of 3, and so on and so forth. So we can also draw the pi MO of ethylene or other molecule in this way. Now we will draw the pi MOs of 1,3-butadiene. Now, as there is 4 carbon atom, 1,3-butadiene, there is 4 carbon atom. That is why we will consider 4 individual p atomic orbital of 4 carbon atoms. When the 4 p orbitals overlap with each other, they form 4 molecular orbitals, and 2 of them is anti-bonding molecular orbital and another 2 of them is bonding molecular orbital. Bonding molecular orbital have the lowest energy, and that is why Shy1 and Shy2 has the lowest energy, while Shy3 and Shy4 being anti-bonding has the higher energy than the bonding Shy1, Shy2 molecular orbital. So for Shy1 there is no node, but we know that for Shy2 there is one node, and the node is along this axis. For Shy3 there is 2 nodes. For Shy4 there is 3 nodes. So when we draw the molecular orbital diagram for 1,3-butadiene, as we are considering the pi molecular orbitals, and we know that for 1,3-butadiene there is 2 pi bond and they have 2 electrons each. So applying Moore's principle, Aufbau principle and Pauling principle, the electrons are filled in this way, and when they get excited it becomes like this. So in the ground state, this is HOMO and this is LUMO, and when they are in excited state, HOMO, this is the highest occupied molecular orbital, that is why this is called HOMO, and or you can say this is SOMO. And as these 2 molecular orbital have 1 electron each, we can say that this is SOMO 1, that is singly occupied molecular orbital 1, and we can say that this is SOMO 2, that is singly occupied molecular orbital 2. But this is actually the HOMO as the highest occupied molecular orbital. So I hope that you understand how to draw 1,3-butadiene or the pi MO of 1,3-butadiene. Now the most important thing where the most of the students get confused, that where to put the nodes while drawing molecular orbitals of organic compounds. Here your 1,3-butadiene. So remember that nodes are positioned in a way such that they are symmetrical relative to the center. A system with one node has the node in its center, and with 2 nodes will have the nodes at equal distance relative to the center. So this is the way how you can put your nodes. So as a summary, we learned from this video what is pericyclic reaction, how to draw molecular orbital picture of organic compounds like ethylene 1,3-butadiene. In the next video, we will learn pi molecular orbital picture of some other molecule. Definitely we will learn acyclic and cyclic molecule. So, and after that we will move on to electrocyclic reaction. This is your lecture 1 of pericyclic reaction. Please like, comment and share, and do not forget to subscribe and stay connected with fundamental chemistry. Thank you.